Угу. Фон називається. Ага, він нас чує. Як він називається, не пам'ятаєте? А, HyperX, да? Ось це. Да, я зараз зроблю ще. О, нормально.
Good morning, good day. And let's start our seminar problems for theoretical business. Usually we organize this seminar in our institute, and this is our available seminar. But today we decided to organize it in field scientists. And because we have from Sweden and from Italy. This is professor
Воно не постійно, де мову прибрухано. Це скрін, а потім розшарить. І ще там скрін. Ви ж вмикали якось. Як F1, помічні? Все, воно там розшарилось. Так, а воно ж, по ідеї, туди видно. Просто треба мишку якось чи праймери мені. Воно тоді тут буде, але воно буде там. А я можу перейти. А, ідейно, ні, навісь, як я розвиваю цю стіну, а це не стає. Спробувати ще раз. Фулскрін, а потім пробувати витягти просто в сторону. Можна спочатку в яку сторону, треба цю мишу тягнути вліво чи вправо, щоб воно. Тоді зараз на фулскрін, а потім спробувати мишу повернути назад. Тоді не вийде. Це буде правильно. Так ми вже намагалися, воно все рівно відкриває на цьому. Тобто зараз спробуєте. Один, воно відкриє. Бо от настройки можна тут. Це та настройка.
You have the this one, you know that one. Where should I stand? Where should I stand? More or less here. Maybe here. Okay. From that side of right here. Yes, yes. Let's just do again. Yeah, you can ask me questions, raise your hand.
Yeah, just started.
Okay, now we see. Yeah. Looks okay. Should we check that this works also?
No.
It doesn't work? No? So. Yeah, thank you. Okay. Should I start? Thank you very much for the introduction and thank you for the honor to be able to give this lecture here. It's a great pleasure. It's the second time I'm in Kiev and the third time I'm in Ukraine in the last few years. A few of you, I think maybe 3 or 4, have heard a similar lecture before in the conference we organized in Lviv together with Larissa Bridget last summer. But I can see that most of you in the audience are new to me, so I hope that you hear it for the first time. So it's not 101 years of thermodynamics, but it's 202 years of thermodynamics. And it's the title as given was 201 years, but I realized preparing the talk that we have another new year, so it's 202 years. I don't speak Ukrainian, but I understand more or less, so I can check that Google Translate does a correct translation, for instance. Of course, I ask. But, yeah, I think with a little help I can check. So it's okay to ask questions also in Ukrainian, I guess, but I will not try to answer. So why 202 years? Now let's see if it works here. No, didn't change. What happened? Right. Again, maybe closer to you. No. Now, yeah. It's because thermodynamics as a science, the birth of thermodynamics as a science is attributed to one book published in 1824 by Sadi Carnot. And I was invited for the 200th, the bicentennial. So 2 years ago, there was a conference that they called Polytechnique in Paris to honor his contribution and his invention of thermodynamics. Here you find the title of his book, so Réflexions sur la puissance motrice du feu et sur les machines propres à développer cette puissance. So reflections on the motive power of heat, but actually the title as printed is not heat, it is fire. But in his handwriting, you can see that his initial title was in fact heat, chaleur. But chaleur, heat in this was at that time not really a technical term of wide use in French. So he changed it to fire in the French one. But the English translation has always been heat, and on machines fitted to develop this power. This was his single only scientific publication in his lifetime. It was published at his private expense in a bookshop, Bachelier, in Paris. And then it was republished much later in the scientific annals of l'école normale supérieure in Paris. This is the banner of the conference, and as you can see, is Sadi Carnot himself as a young man. I will say a little bit about his life story and his young man as because he died very young. This is the first page of his original publication. Now let's see. So, sorry, there should be this. There's this, of course, why thermodynamics and not any other? Well, for one reason, there is this famous quote by Einstein, which I'm sure all of you have seen, or most of you at least have seen. He discusses his early scientific interest and development, and then says about thermodynamics, about classical thermodynamics, that is the only physical theory of universal content concerning which I'm convinced that within the framework of the applicability of its basic concepts, it will never be overthrown. And of course, this is quoted very often to tell how intrinsic to physics is thermodynamics. And usually the thermodynamics today is taught, at least if you have a physics background and not an engineering background, as a consequence of statistical mechanics. And you can see here 5 people who are made the most important contribution to this science in the 19th century. And let's say for the young people in the audience, anybody below 30, okay? So let's start from the middle one. Who is that? There's Maxwell. And who's the next one? The one with the sort of green jacket. Who's that? Of course, yeah. And who is the one to the right? Of course, yeah. And then you already know who's the one to the left. That's Carnot. And who is the next one, the one with the other? He is? He is Clausius. So you all know. Very good. So today I will focus on the contributions of these two gentlemen, because the way we are taught thermodynamics is from statistical mechanics, which are the last 3 gentlemen. These 2 gentlemen, and I will tell a little bit on the view of Clausius on the basis of thermodynamics, but not so much. But these are the contributions of these 2 gentlemen will be the focus today. So what is in this book is a very beautiful French. If you can read French, it's kind of a pleasure to read just the formation of the phrase, the precision, kind of the old culture. And here I've quoted for you. I will not read this sentence in the entirety in French, but this is the opening paragraph. And I've translated it for you with the help of Google. He wants to understand steam engines, heat engines. And he was, as you can see by the date when he was born, he was 36 when he died. He was a military engineer, educated at École Polytechnique, and the only title he gives in his book is a former student at École Polytechnique. That's the only title he gave. He was at the time at the French General Staff, and you can imagine then that he was a very busy military person. No, not at all, because for reasons of politics, this was after the end of the revolution. They did not give him any substantial things to do. So in his spare time, he got interested in heat engines, and eventually he then wrote this book on which his fame rests. And except for the opening for the French, there's actually more to be said about this. Why is steam engines so really important? Why was it important to Sadi Carnot at the time? Because English steam engines are so much better than French steam engines. His father, Lazare Carnot, here, that you can see here, was an eminent scientist in his own right. He wrote some books on the theories of machines and on the philosophy of differential calculus. He was also a politician, and he was a general in the French Revolution. He was, for a while, after the end of the Robespierre terror, he was the member of the Directoire, which was the government in France at the time. And at the time of Sadi Carnot's birth, he was in fact the president of the Directoire. So he was living in one of the big palaces, the Luxembourg Palace in Paris. If you've ever been to Jardin de Luxembourg, if you've been to Paris, it's a beautiful park with a beautiful palace. And this young gentleman was actually born in that palace because he was the son of the then president. A few years later, Napoleon came to power, and this gentleman retired to private life. Then he came back and served Napoleon towards the end, and of course was exiled by the new government, and he died in exile. So the main reason why Sadi Carnot, even though he had the perfect French curriculum, entered École Polytechnique, which was actually founded by this guy. So he's the founder of École Polytechnique also. So he entered at the age of 16 and then came out very early with perfect grades, had a perfect career. He was not given any substantial commands or responsibilities in the new army. And therefore he had time for science. So here is also from the fourth page, and there are many of this. I've here highlighted, of course, the word England, because that was what they measured on. And you can see here a number of names of, at that time, quite famous engineers in the field of steam engine. And of course, we all today know about Watt, because we have the unit of Watt. Maybe if we have read a little bit more, we have heard of Newcomen, because the Newcomen steam engine is sometimes quite well known, but you have to be really a specialist to even have heard of today of the steam engines of Savory, Smeaton, Wolf, and Trevithick, whatever they were. But these were the things that he wanted to measure. So he had this practical question: why are English steam engines so much better than French steam engines? And of course, why did we lose? And then by meditating on this question, he comes upon the scientific question. What are the theoretical limits of the performance of a heat engine? Can they be arbitrarily efficient? Does the medium make a difference? Does it matter if you have water vapor or you have the atmosphere, air? And would air be better than steam? And that's I've highlighted some key parts of phrases in French, which more or less expresses these things. Is there a limit? How well can you make it? And then he proposes that this is now what I'm going to give you. I'm going to give you the theory, the science of thermodynamics, and I'm going to tell you how good they can possibly be made to be. Then there is also in this paper a clear statement, which was chosen as the title of the conference. The theme of the conference here is the part. You can see his own handwriting. That was the standard handwriting at the time. People knew how to write well and pretty. that the production of heat alone is not sufficient. This is a translation of the phrase into English. The production of heat alone is not sufficient to give birth to impelling power, that means to produce work. It is necessary that there should also be cold. Without it, the heat would be useless. So it's the temperature differences that drive motion that you can use as it were. This is a central result in. He also introduces the Carnot cycle, which we all teach when we teach statistical physics, and we explain on the piston which parts which are in contact with the heat mass at the colder temperature, at the hotter temperature, and the adiabatic compression and expansion. And here is his own illustration of the Carnot. However, the Carnot diagram, the PV diagram that we also teach, you cannot find in the book. And to be quite honest, the math in this book is almost impossible to follow from a modern point. This is clearly pre-modern and it's really difficult. Other things is he states a general principle, which is the answer then to the question, to the scientific question, that the maximum performance that you can get out of heat engines only depend on, that doesn't depend on the medium that you use and depends only on the temperatures of the bodies between the heat has been transported from one to the other. But from the viewpoint of today, you would really not call this a result. You would call this more or less a principle, an axiom. It is established by reasoning of the motion of the piston. You cannot find the Carnot efficiency in his book. It's unclear if he actually knew it, because after publishing this book, he eventually resigned from the general staff. Then it's unclear, at least you ask a specialist in Paris, but apparently he had some psychical problems. He was probably in the private asylum where he died out of cholera. And almost all of his surviving papers were burned after his death for this reason. So it is possible that he knew about the formula of Carnot efficiency, but never published it. But that is probably, at least he didn't publish it, so it was rediscovered afterwards. One also imagine, and that's in the history of science, one should imagine that one should also take into account that Carnot imagined heat to be a kind of fluid, which he called, of course, caloric. And we know now, of course, we know since a very long time that this heat is not a fluid. Heat is the disorganized motion of molecules or atoms, so that you cannot control from the outside. So the thermodynamics, as developed by Carnot, and that goes also for Clausius, is based on a microscopic model of heat, which is actually incorrect. But still, the results of the microscopic thermodynamics are the same. So this, I hope I've stimulated you, if you like French, especially French late 18th century, early 19th century texts, and if you feel comfortable about skipping the mathematics, then there are quite a number of nice phrases that you can read in this old book. Let me go to Clausius, and it's quite interesting. This is 200 years ago, and you see the difference from what we would call an amateur, in the sense that somebody who loved science and developed science by himself. He, of course, had a wonderful engineering education for his time, but he was not a professional scientist. He was a military man doing science in his spare time, compared to an academic who had a brilliant academic career and who writes more or less as a modern academic. You can find some kind of, in the notation, it's not, especially in differentials, is not the modern one, but he actually has, if you read all these parts of what Clausius did, he has an explanation where he understands the differences in the differentials very clearly. It's just he hadn't invented the modern terminology. So he wrote 9, also it's among many other academic careers, he was also president of his own university. He was the elected member of the Swedish Royal Academy. He was also given the Iron Cross of the German Empire because his services when he was almost 50 years old. So he wrote 9 memoirs on thermodynamics, and they're collected in a book. And every physicist, of course, knows that he invented the word entropy. But what led him to do it, and how did he do it? So now I propose to you to follow a part of this of these 9 memoirs that he published in this book. This is the English version of the book, which is published in 1867. He published them with a commentary, with an introduction. Before I talk about this statement from the introduction, Clausius is quite remarkable in the sense that as his time, of course, science was split between the German part, the French part, and the English part. And he either translated himself or had it immediately translated, all his original work in German, into French and English. So for almost all of them, there is an almost simultaneous date of publication in a French journal, in an English journal, and in a German journal. So he knew how to, make his work appreciated all over the world, and he took the effort to do it, which is now, of course, more than 150 years ago. I think this part of the introduction is quite interesting because it shows, it's also published in 1867. It exposes quite clearly that Clausius' point of view of what is heat is more or less the modern one. If I read for you, other memoirs, again, which are not among the 9 ones in thermodynamics, have reference to the conception I have formed of the molecular motions which we call heat. Those conceptions, however, have no necessary connection with the general theory of thermodynamics, the latter being based solely on certain principles which may be accepted without adopting any particular view as to the nature of molecular motion. So there is a shift then from Carnot to Clausius, and what Clausius is saying that as concerned the thermodynamics, which I will develop in this book and which had been developed in these 9 papers published in the decade before, I don't need to separate which of these 2 theories is the right one. For the thermodynamics, which I will develop, they are the same, or they don't matter. So with this, let me go through and a little bit inspire you to read these old memoirs. The first one, which was published in Annales de Physique and in Philosophical Magazine, there's also a French publication, around 1850. He introduces a maximum which he attributes to Carnot. It's not so easy to find directly in Carnot, which says that heat is a form of energy or as work. And so if heat is measured in the amount, heat is measured in units of heating a liter of water of 1 degree Celsius at more or less some temperature around the freezing point of water. And work, I will get to a moment how work was measured at the time, not in Joule. So it should be, these are 2 different units, and there is a universal constant which he calls A, and which will appear again. And after 2 different calculations, one not so exact, which is easy to follow, and one more exact, which is, one not so exact, which is easy to follow, one not so exact, but one exact, but not so easy to follow, he finds the value 421. And so you would expect, why not something like 4,000? Because work, according to Clausius here, was the amount of work you needed to lift 1 kilogram, 1 meter at the Earth's surface. And of course, there's acceleration, which is almost a factor 10. So this number here, 421, is more or less the relation between Joule and calories that we got, with a factor about 4,000. And then he does a comparison to experiments which had been done by Joule. So here's a calculation. There's one based on steam. That's the precise one. Difficult to follow. There's one based on the ideal gas, which is more easy to follow, but not so precise. And then there's different experimental measurements for this number. And of course, he's pretty close, especially the last one on the friction. And this one is correct to 2 significant digits. And this is what made Clausius, I think, a scientific star. He was able to compute as a theoretical physicist what the experimentalists had already measured. And he also introduces the first law in heat being change of internal energy. And here is this conversion factor. And of course, this is work. Yeah, so with sign convention, you can find different ones, but that's the sign convention used by Clausius. So this is a really interesting and very easy to follow paper. You also find the PV diagram. Here's the infinitesimal PV diagram that uses in later memoirs. Then I skipped the second and the third memoir because they are more about steam engines and not really pertinent to the question here. The fourth memoir is really important. He states the second law as a principle, that you cannot take heat from a colder body to a hotter body without any other change. And he introduces a statement that two reversible processes are called equivalent if they can be replaced by the other one, and are then characterized by an equivalence value. And this equivalence value he calls equivalence value in German, which is Äquivalenzwert. Using a Carnot cycle, in fact, a slightly modified one with 6 stages, but that's a detail, and the principle of second law, he finds the equivalence value to be heat over temperature. But actually, he says first, big T is some undetermined function of temperature measured in degrees Celsius. And then he has this formula for a cyclic process and reversible cyclic process. And at the end, he argues by the example of an ideal gas that probably its temperature is absolute temperature. That is the temperature in degrees Celsius plus 273. And here's a little bit of his style. You can see that it is a more or less modern style in the presentation. It's like a very learned and very original colleague talking to you. So this fourth memoir, I think, is a fantastic paper. Then on the fifth and the sixth memoirs sort of continue. There is a statement of the Carnot efficiency, which really, of course, is the work. Here is the quantity A, which is his exchange factor between the units of heat and work. There's the heat, and then there's the two temperatures. Right? There is also, in the 6 memoirs, there is the inequality, which we now recognize as a quantitative form of the second law. And here you can see an example of where it's published. So you can see you publish a publication here in Philosophical Magazine, in Poggendorf Annalen, and here is Journal Math Paris. And you can see all of this is probably, most of it is translated by himself. Then comes the 9th memoir, which contains 3 things, I would say, only. It contains a new word, entropy, instead of Äquivalenzwert. It contains a new symbol, which is S. And it contains this famous last conclusion of the paper. And I think it's fair to believe that this is a large part of why Einstein considered thermodynamics to be such an important science. For the present, I will confine myself to the statement of one result. If for the entire universe, so he went from steam engine to entire universe, we conceive of the same magnitude to determine consistently and with due regard to all circumstances, which for a single body I have called entropy. And if at the same time we introduce the other and simpler conception of energy, so energy was at that time a reasonably new construct, even though, of course, Newton's 4 laws have been known for some time, we may express in the following manner the fundamental laws of the universe, which correspond to the 2 fundamental theorems of mechanical theory of heat. The energy of the universe is constant. The entropy of the universe tends to a maximum. And even today, after so many years, there's more than 100, now 170 years, something like that. No, 100 and, okay. So, well, it's more than 150 years. It is still rates as one of the most concise and but still wide-reaching conclusions of a paper ever published. But it should be seen not as the conclusion of this one paper. It should be considered as the conclusion of his own investigations into the nature of heat and how to use it. Well, then this was in 1865, and then soon after was the French-German War. Then he was severely wounded in the war, and he never came back to work in science on the same level. And unfortunately also got involved in a lot of disputes on priority with Boltzmann and many others. But that I think doesn't really pertain to his great achievement, which are these 9 memoirs ending with this very, very wide-reaching statement. Still basic physics as of today. So why consider thermodynamics today, except as a field in of history of physics? Or why consider thermodynamics separately from statistical mechanics? Because of course we learn, and at least that goes for me, probably for you also, for many of you, we understand thermodynamics often today as a consequence of statistical mechanics, which is what we understand better. And we are a bit uncomfortable if I'm extrapolating from my own experience. When you start working with it, with these concepts, what is actually heat, and how do you express heat, and why should you reason in terms of heat and work and not energy and states, which are things which are for the modern time, for most of us in the modern time, more familiar. So I will give you first rather mostly to amuse you a little bit in engineering. Scott Ford is a first example that it is often in particular in optimizing an engine, as you can see you will see on the next slide, Carnot efficiency is often not the most relevant quantity, and this is something which can be understood quite well in discussing things in the language of Clausius and Carnot. And then entropy of production environment, which is really using Clausius' formula, and has been an extremely important research topic in statistical physics in the last 30 years, and which I also been interested in and worked on, and I will tell you a bit about this. Maybe here some divertimento on maybe we have other things that could be of interest, and if we get it to make a connection to the presentation to my colleague, Carlo, I will also say something about the fourth example. Yeah. Okay, so this is the plan of the rest of my talk. Now, so history of science, old history of science is mostly over, and there will be now some more recent history of science. So first example is the concept of efficiency at maximum power. And this is based on a Carnot efficiency is achieved for a reversible process. This means that it's slow. Power is work done per unit time. It is hence 0 for a reversible process and for a Carnot engine. So a Carnot engine is useless. It cannot be used for any practical purposes. If you put it in your car, you'll never get anywhere. Well, at least not in your lifetime. So a very fast cycle is, on the other hand, practically the same as a direct contact between the hot bath and the cold bath. So a very quickly cycle, that is also a Carnot cycle, which goes really, really fast, also has 0 power. So the maximum power is somewhere in the mean. It's somewhere in between infinitely slow and infinitely fast. And efficiency at maximum power, this is how efficient is the machine which works at maximum power. Of course, it cannot be better than Carnot, but how good can it get? And it turns out this is a field of science in itself. There was a very nice review with a review volume with many contributions of people who worked on this from the French Society about 10 years ago. I stole this wonderful illustration of a heat bath and a heat engine. Yeah. Mr. Chairman, tell me what to do.
So dear colleagues, you have just
Oh, it's my own.
Maybe the spike comment. So I think we can continue.
Okay, so dear colleagues, who wants can go downstairs, but if there is no objections from our lecture, we continue, and
I am your guest. I'll do as you say.
so
Yeah.
Eric, we would like to ask you to continue.
Thank you. Yeah, I mean, so of course, if you have the Carnot engine, let's think about the Carnot engine, and you say, okay, I put it into contact with a heat bath, say at a lower temperature. Then the temperature of the Carnot, of the heating, of the working fluid of the Carnot engine cannot then be the same as the reservoir, because if it were, there would be no heat flow in between them, so there would be no heat exchange. So there must be a different temperature on the heat engine when it's connected to the hot temperature, which is not the same as the reservoir temperature, and the same thing, of course, on the cold side. So there is a time element in how long time does it take to transfer a amount of heat over some heat exchanger with some thermal resistivity, given a temperature difference on the heat engine, or if you prefer on the side of the heat engine towards here at the connection point to this heat engine. So that brings a natural time scale. And if you optimize over all of these things in linear thermodynamics, so everything close to equilibrium, you will find that, and that is the main claim of this field, that there is a maximum efficiency, which is 1 minus the square root of the two temperatures. So remember, in the Carnot efficiency is 1 minus the ratio of the two temperatures. So the ratio is changed to the square root of the ratio in this kind of model. And that's usually attributed to two American physicists, Curzon and Albom, who published this in 1975. And it's a start of it was brought up by Chris Vandenbroek, the late Chris Vandenbroek, who was one of the main players of this efficiency of maximum power in many different models in a famous paper in 2005, and which has led to an enormous literature. So Chris Vandenbroek called it the Curzon-Albom formula, but as pointed out by many people, this formula was known in nuclear engineering before. And in particular, there are two French physicists and nuclear engineers, Yvon, who is well known for, also I am sure here in Kiev, for this association with the method also at Bogalyubov, and Chambardal, published at the end of the 50s. And there's also a Soviet physicist who published at the same time, slightly later, but more or less the same. And so this formula was known well before Curzon and Albom, and is new to engineers. You can then argue, is there something specific about nuclear engineers? No, there was an engineer who wrote in French, who was Belgian, who publishes in 1929 this formula. And you can see here, this formula, this is the Curzon-Albom formula published in 1929. And it's about, of course, the best utilization of heat engines using coal. And it's cited, there's this very nice long, especially this in this volume from the French, the review paper by Moreau and Pommeau, the rather famous French physicist Pommeau. They have this story, and especially this one, which is easy to find. They also claim, this is less easy to find, they claim that there was a French thermodynamicist who in 1862, which is only like 10 years after the publication of the Carnot formula by Chapelier, or 15 years after, that he published, but I have never found this book, so I cannot really vouch for that this is true. But apparently this man, who had a very Swedish-sounding first name, Gustav Adolf Irne, and here to show that he was considered once upon a time a very important person in Sweden, is a long entry in a Swedish encyclopedia published in 1909. He was in fact also elected to the Swedish Royal Academy of Sciences, and before Clausius. So at that time he was considered greater, but then I think it's fair to say that he is almost completely forgotten. But apparently this Curzon-Albom formula was perhaps invented already in 1862. And all of these things can be understood not in terms of the entropy of statistical mechanics and Boltzmann and Maxwell, that they are clearly within the entropy and the second law of Clausius and Young. That's the first example. Second example, and maybe Mr. Chairman, you should tell me how much time do I have? Should I kind of speed up or?
Mr. Chairman is on the phone call.
But then you
may show.
yeah. So I can go on.
Please take your
Yeah.
time.
Yeah, Chairman is not here, you can
Okay.
do everything you want.
Okay. Very good.
Even to be a Chairman first.
Okay. Yeah, I think this. I never worked on this efficiency and maximum power myself. I prepared this this part of the lecture when I gave it the first time, and I think it's quite charming that perhaps the first invention of this formula, which was reinvented in 2005 by Chris van den Broek, and attributed to Curzon and Alban, were two American physicists publishing in the 1970s. In fact, was published in the 1860s.
Yeah.
By a person who at that time was really, in fact, maybe he was slightly, part of the reason he became so famous was that he was the first cousin of Haussmann, who was the great architect of Paris. So, you know, who redesigned Paris and built all the boulevards in Paris. So he had wonderful family connections, but he was very likely also a very important person in his own right, but of course cannot be compared to Carnot or Clausius, his impact on physics. So I will tell you a little bit about things which I will also get a little bit of things I worked on myself, but to tell you something about time reversal, and which is of course very fundamental for conservative motion, for Newtonian motion. So let's consider here Newton's equation of motion, non-relativistic. The velocity is the partial derivative with respect to momentum of a function, which we call the Hamiltonian or the energy function. And the time derivative of momentum, so force, is minus the partial derivative of the Hamiltonian with respect to position. But we let this Hamiltonian to be time dependent. So there's a driving parameter here, lambda, which is a function of t. And we consider a protocol which starts at some lambda I and it ends at some lambda final. So this is my protocol, goes this way. And here's my reverse protocol. That means it starts at the final position here is the initial point here. And the final position here is the initial point here. Then we know from elementary mechanics that this process is time reversal independent, in the sense time goes to minus time, Q goes to Q, P goes to minus P, Hamiltonian goes to Hamiltonian, force to go force. So these equations of motion are reproduced for the time reversed ones. Okay. Of course, this means this has a time derivative that when you start, this means the reversed motion is that you start with your protocol at the final position of the forward process, and you have the same position Q and you have the opposite momentum. And then you go backwards, changing the protocol in the reversed order here, and then you will end up here at the final time going in the backwards protocol, which is the same as the initial position in the forward protocol, and you'll have the same position and you have the opposite momentum here. So if you reverse momentum again, you will be backwards now. That's time reversal in classical mechanics. So if you now have a system interacting with environment in stochastics, then what is our the most simple model? It's of course the Kramers-Langevin equation, or the underdamped Langevin equation, where you add to conservative motion a friction force, which is this one, and a random force, which is this one. And this in the Langevin equation, the random force is delta correlate. So in this case, let me take time goes to minus 10, Q goes to Q, P goes to P, force goes to force. However, the friction force here, it goes to the same. Well, it means even though the friction force is written in terms of P here, So P goes to P star, which is minus P. So here's P goes, this force here, it goes to the same. So the conservative forces and the friction forces are not time reversed in the same way, which we know. And if you do this, you will find a time reversed stochastic equation, which has friction. If you time reverse this as the other way, if you would put a plus here, you would of course not have a friction force. And it's well defined as a mathematical problem, but it's not well defined because it's just a stochastic differential equation, but with an anti-friction. But an anti-friction is not physical. Okay, so this is the time reversal called in this wonderful both review and summary of a lot of work by the two French and Polish physicists, Chetit and Gawęcki, now close to 20 years ago. This is called the canonical time reversal. And in this, you can consider then path probability ratios. So the path probability ratio is the forward probability versus the reverse probability of a path in position and momentum. So here's position, and the Q star and the P star are the time reversed according to the previous picture of the Q and the P. And the path probability, that's what you have, the probability of observing a certain path when for the forward path, you're following this dynamics, and for the reverse path, you're following this dynamics. Of course, it's a kind of Gaussian, of course, because it's a Gaussian randomness. And you can do some mathematics, you can do a little bit of massaging this thing, and you find that this ratio of probability distributions, in fact, is 1 over QBT and the heat exchange in the forward process between the system and the bath. There's a Japanese French physicist who pioneered this kind of thinking, Ken Sekimoto, and it ends up by saying that you can get some exact results, of which the most famous is this one, the Jarzynski equality, and the second most famous is this one, which says that the average over the realization of the noise driving the process of exponential minus the total entropy change. This is both entropy changes in the environment and the entropy change in the system, is in fact a fixed number 1. So this gives, in this case, the second law as a consequence, as an inequality. And the number of people who worked on this is quite long. The first noting of this kind of equality, but in the special case when the free energy difference is 0, is in this paper by two physicists, one working in Russia, one in Ukraine at the time. It's already in 77. It's clear this is not a very clearly written paper, and the statement was then, in the more general case, was rediscovered by Chris Jarzynski, an American physicist, and that's usually attributed to him. He was the one also understood the fundamental importance of the equation, but you can find the equation earlier. And here are some other references. There's also now a textbook by Udo Seifert, is a German physicist who discovered this equality. And there's both a wonderful long review, and there's also now a textbook by him on this topic. This has been a major focus on stochastic, in statistical physics in the last quarter century. And when you come into this field, which was, for me was about a bit more than 10 years ago, maybe let's say 15 years ago now, then you are really a bit unused to having a reasoning which starts from the concept of heat. And that's really necessary here. There's also this very nice statement, which is really due to Chetit and Gawęcki above all, that entropy, which is entropy production in environment, so heat exchange with the environment in unit of kBT. If you take the logarithm, the exponential goes away. So there's one way of writing it in terms of the action of the system according to the laws of motion. That involves the action of the friction force and the random force. And you can measure it entirely as a function of the system. You can also consider it more abstractly as the logarithmic ratio of these two probabilities. So there's two different, which are the same for these. You can do it's not such a. Yeah, it's sorry. Now it doesn't seem to go back. Maybe I should go further. Now it goes forward. Okay. Now you go forward even further. Okay, let's go forward. Okay. No, it's fine. It's fine. I just okay. Let's say so. Here's the flagship application, which for this theory, just to remind you, Felix Vitort in Barcelona has been one of the leaders in this field, at least in Europe, I would say even worldwide. So you can pull apart single molecules, and you can measure the force on these molecules because usually they are made by optical tweezers. You know where's the focus of the optical tweezers. Yeah, and you can the equilibrium point, and you can also measure this actual point, and then by proper calibration, you know the force exerted by the bead connected to the molecule. So you can do force extension curves, and by these force extension curves, you can measure the work done in such a process when you extend a molecule and when you compress a molecule. So this has been done both for DNA unzipping and zipping proteins and unfolding of RNA and DNA and RNA hairpins. It has not been such a success that it has substituted all other ways of measure these ones. They're kind of there is the delta F, delta G, which is usually so you change, you do some biochemistry and change some of these bases, and then you can measure, especially in complicated conformations, you can measure those delta G's by this method better than others. But it's also interesting that it can be done on the level of single molecules. So these you can, with modern methods, you can repeat these measurements thousands or maybe more than thousands of times. You can get pretty good statistics on the work, sufficiently good that you can then measure these, even the free energy changes. Not using Jarzynski equality typically, but using another related equality in the same family. And there are also some solid state system with pioneered by Jukka Pekkola in Helsinki, where you can easily do how many trials you want on this. So you can have statistics of millions or even more, and you can get very high accuracy. So for these systems, the Jarzynski equality has been verified to many significant things, which is a way of saying verifying a mathematical theorem in a physical experiment, but still it has been done. So that's really important. And I will continue a little bit on this second example. So now suppose we are interested in the minimal entropy production. So suppose we have a two-state system, two wells. So we start having a well, there will be a well on the next slide, but you can imagine a well here. And suppose it's uncertain in which well is the state. And then you make some transition, you move over all the probability mass to one well, and then you change back so that it actually is now a two-well system. That is like setting one bit of information, classically. And since the total end by the principle of the second law, the total entropy cannot increase in expectation, but that's, let's say, the expectation version, the stochastic thermodynamics version of the second law. Entropy in the environment must satisfy this equality because there's a reduction by a factor 2 from 2 wells to 1 well. And that means that there is a minimum released heat to set one Bell bit in a classical computation, which is kBT log 2, which was already proposed by Rolf Landauer in 1961. And so here, this one, you can then say, okay, it's a little bit on the same side on the efficiency of maximum power. Suppose you do this in a finite time. And suppose it's over damped diffusion, which is Landauer's original example also. But suppose that we do it not infinitely slowly, but we do it in the final time. Then there is a result, which I will come to a little bit later, that the minimal entropy production from one state to another one is in fact Landauer's plus a correction which is inversely proportional to the time that it gets. This is the kind of result that you can get in this science. And I was involved in finding this result and I will spend a little bit. It's now become a much larger field with many others working on it. But I will come back to that. There will be an interlude talking on a related problem to my late compatriot Göran Lindblad, who's famous for the Lindblad equation in open quantum system. He also wrote, this is a picture of him at around the time when he defended his PhD thesis and invented the Lindblad equation, and this is a picture towards the end of his life. He wrote one book in his life, which is about non-equilibrium entropy and irreversibility. And it's not been very highly cited for a long time, but now it starts to be reasonably cited. And in the we edited a memorial volume to him, since after all, the Lindblad equation is, one must say, the most important contribution of any Swedish physicist to quantum theory since the beginning of quantum theory. And he did not get proper recognition either at my university or in Sweden for this during his lifetime. So we decided to add to edit the volume. We have contributions of many people. But in particular, somebody had to write something about his book, since he only wrote one book. And since we couldn't get anybody else to do it, I did it myself together with my colleague Ryoshi Kawai. So I happen to know a little bit what's done in this in this book. And it's a technical book, it's a book about quantum, but it has an aspect which repeats this Landauer principle and the statement of minimum entropy production, which I will try to bring across to you. So he defines what he calls a P entropy, and the P entropy is the minimum. You start with the state, which for him, of course, is a quantum state, but we can think of also the classical limit of a quantum state. And then you consider a manifold of Gibbs states. So these are the thermal states. And the P entropy for Lindblad is the minimum over all Gibbs state that you can get to of the change of the information theoretical entropy. That means the statement that will mean the famous rho log rho minus rho log rho, going from here to here, and the amount of entropy production that you effectuate in all the reservoirs could be more than one connected to the system. So these are the ones then in the Lindblad equation. If there's a Lindblad equation for the evolvement of this density matrix, these are the one that gives rise to the Lindblad operators and that part of the dynamics of the system. And here you can also see that it's basically the same definition as we have. This is taken from his book. It is the inverse temperature of that reservoir, and there is the change, the energy change in that reservoir. It's the same Clausius definition used in as the basis of the discussion of stochastic thermodynamics and time reversibility. So this is kind of complicated. It's kind of impressive that he manages to prove a number of entropy-like properties for this P entropy. And I think this is unfairly, overlooked as a contribution to mathematical physics and to the foundation of stochastic thermodynamics. I'm therefore happy to, in all occasions that I can, to pull up this statement of my illustrious, now no longer present with us colleague. But my focus today will be on the entropy production in itself, and especially in the light of classical problems. So suppose that this accessibility, this means all states that you can get to, including these Gibbs states that Lindblad was interested in, means all the classical overdamped Langevin controls at some time t, or maybe underdamped. That theory has been done also later by others than me. Then this P entropy, in fact, is the same as these minimal entropy production functional, which we were happy to discover that it is given by also minimal transport distance, and this minimal transport distance is the same as the Monge-Ampere problem in the 18th century. In fact, both Monge and Ampere were teachers of Carnot at the École Polytechnique. Here is a kind of it's also a military problem. It's how do you, with quadratic cost, how do you move some earth from one place to another place, because you wanted to build fortification. And as far as we know, there is a special, there was a fishery of letters by Seifert and one of his students that found a special case of this, that we were happy, we were able to, 15 years ago, we found this more general result. And I also have this more general paper together with Krzysztof Gawęcki in the year afterwards, and then several others have worked on it, and Dago Chilaberto and Brosmans and Bernhofer group. Apparently, this is actually, I mean, this equality between optimal entropy production of a stochastic process and an optimal transport problem was first noticed by mathematician Villani in 2003. But this is really difficult for a non-mathematician to actually make sense of. When you were out, Mr. Chairman, I asked when should I stop?
Well, you have 5 minutes.
I have 5 minutes. Okay, good. Okay, so I will say a few things then. Okay, so actually this is experimental data from a famous paper by the Chilaberto group and others in 2012, which was a big inspiration for us. You can see here that you move over the probability mass from one place to another one. And it turns out that this optimal transport process for an oscillatory field, which we here call psi, is governed by a famous equation in fluid dynamics, model equation, the Invicit-Burgers equation. So the Invicit-Burgers equation for a given initial density profile and final density profile is not something which is often seen in hydrodynamics, but in cosmology, at least in addition model, which is a kind of subclass of model which comes back to the Lowick school. This problem was considered already some years before by Frisch and collaborators. This would be a picture of the initial condition being what you see from black body radiation, and the final one is the galaxy mass. And if you believe that the initial dynamics is governed by, of course, this is an approximation in the real universe. It's one in the series, the simplest in the series of application. You have the same model problem. So we were able to use the same numerical code for our problem to solve this one, to find the optimal one, because Roya Mohaye, who was one of the co-authors, was also the one who developed this code. That's one connection to your work. So cosmology is also useful for the mesoscopics. That's the one thing. So let me say a third example, and I guess I will not get to the fourth example. So do we have engines of today? And I like very much this example, which is now really quite old. It's almost 6 years old, but there was this wonderful website called This Person Does Not Exist, which at that time was able to generate faces. Of course, today we can generate movies, and if you like to watch Twitter or similar things, every day there is a new movie of some ridiculous person, maybe with a very important position, who makes something, maybe he's on Greenland and claims now to be the emperor of Greenland or something, and it looks very much like the real person, but at the time they could already make likeness of people who don't exist. And this is now an important industry, which is almost entirely dominated not by the English, but by the Americans. So the only companies here which are not originally American are this one, AMD. Well, of course, it's American now, but it was first Finnish. And I know this quite well because my son works for this company. So Silo AI, Finnish company, and it's now bought by the AMD. So it's now part of the AMD. So they're making AI for chips, for AMD chips. And this one, which is Mistral, which is French. But mostly this is now an American, for the moment, it's an American market. And of course, it's not only commercial, not only this, it's also the basis of Nobel Prize already several years ago now on the prediction of protein structures. These are the famous citations for the using these kind of machines to predict things of immense importance for biochemistry, for biological physics, for pharmacology, for molecules, for understanding the life. So, do we know how these machines work? Now, I would say that we know that they work because there's an enormous amount of empirics. Like the English knew how to build steam engines. It's quite possible that they also work as well as they can, like the English steam engines of Newcomen and Watt were close to the optimum, although they did not have the theory for it. But we do not know how they work, and we don't know why they work. So we don't know why deep learning works so well for so many commercial and scientific tasks. And here you can adapt. I have it here in Carnot. This is the first statement of his. This is the following statement on page 2 of his treatise, where I have changed steam engines to learning engines, heat machines to artificial intelligence. Here is a translation into English, and with the help of the American translation engine checked by me is the translation to your language. So I will read it in English. Nobody can ignore that artificial intelligence can be the cause of change, that it possesses great power. Learning machines so widespread today are a clear proof. The study of these machines is of the highest interest. Their importance is immense. Their use increases every day. They seem destined to produce a great revolution in the civilized world. And with this, I believe I can end. And I will skip the line.
And we have a time for questions, probably somebody please.
One comment and one question very quickly. So thank you for the impressive coverage of the relevance of statistics and complexity in physics. It's extremely modern and so it is really fascinating. The comment is concerning cosmology. I completely confirm what you said. Cosmologists were happy with a little bit of complexity about 30 years ago with the models of the inflationary universe, etc. Then they were so happy with the minimal modeling that they stopped investigating in detail, and then they derived consequences, observations, etc. Now the era of observations is ongoing, so it's probably there is space for complexity and statistics to come back into play from the theory point of view. That's my comment. So that's something which is coming with several conferences have heard points of similar relevance. And the second part is the last part, which I loved of your vision concerning the relevance for these studies in what we are living today, the situation with autonomous, with let's say, I don't like the word artificial intelligence, so certainly but the digital entities, the digital intelligence or entities which are coming. And the question is the new project situation in the future. So how the theoretical investigations can help guiding the direction given the initial conditions that we are seeing. It's a very uncertain question.
Maybe I can give a comment on a personal comment on this last thing. So maybe if anybody checked my Google Scholar page or something, my best cited paper in my whole career was about finding a way to predict amino acids, so residue contacts in proteins from learning a model in the Gibbs-Boltzmann class. And I introduced in that problem another way of doing this inference thing. And so that means we assume that the distribution of sequences are independent draws from a Gibbs-Boltzmann model in a class of, they call it family, a family of similar proteins. And then we say, if there are strong connections or interactions, we would say in physics, because the two columns are really have a strong interaction in the kind of icing model that you derive, then this is a good prediction that they actually are close together, because then they cannot develop independently. If you change one amino acid, you change the local environment of the other, and then this environment is. And we don't know still after more than 10 years why this really works. It works better than correlation, much better. Of course, after a couple of years, the bioinformaticians found other ways to do it better. And now they can do it infinitely better with deep neural networks. But still, we did not manage, we don't to this day, we have only diverse ideas why it works in that problem. And so for deep neural networks, I think it's a really big and important problem to understand why they do work. Not only that they work, but how they work and what is the limit. Yeah. So I also have a personal interest in this question.
Thank you. Other questions? So please, and after that,
I would like to ask you a very simple question. First, the efficiency of Carnot machine is equal to difference between high temperature and lower temperature divided by the high temperature. Yeah.
Yeah.
Yeah. And you present some other alternative, or maybe or maybe modern formula for efficiency. And as I grasp it, it's difference between higher temperature and lower temperature divided but to the square root of product. Yeah.
No, it's a square root of all the temperatures. In the way you write the formula, you said one temperature minus one other temperature difference divided by temperature. Okay.
Yeah.
So if you take instead square root of everything, square root of temperature divided by square root of temperature, that's the Kurzon-Alban formula. Which of course makes worse efficiency. Yeah, yeah. Yeah, it cannot be, it is not as good, but it has higher power. So it works at the finite time.
Yeah, but I imagine that in denominator stand product of higher and lower temperature and square root. It's nonsense. Yeah.
Yeah. But that's not the problem.
It gives rise to infinite efficiency. Yeah.
Yeah. But that
Okay.
does not happen.
Thank you.
That does not happen.
Thank you very much.
Eric, thank you so much for your interesting talk. As I told you every time, I find something new and interesting, challenging. This is more very general question. Do you think that the study of the neural networks, and I like your from digital intelligence. Yes. This yeah. Useful for our understanding of the emergence of consciousness.
I don't know more about this than you do, huh? I would say following. So I know a bit, and I published a bit on this, but it's now a long time ago, on detailed models of neural networks for model organisms, say the lamprey, which is a very simple fish. We wrote a couple, even one quite reasonable paper, some not so reasonable, but anyway. So, and that is a big activity only in Stockholm, and I think it's a big activity worldwide to do. And that brings you to the realm of writing large systems of coupled order differential equations. Typically, one, depending on what detail you want, how many compartments you include of every neuron, and then you can have also transmissions if they're very far dendrites. So there's infinite amount of detail and complexity that you can add on this one. On how these work.
Complexity.
Yeah, complexity not in a good sense. Complexity in the sense that you get more and more parameters which you usually don't know. And I think these studies, to my extent, to my knowledge, I mean, what I have seen a bit from afar, a little bit, but now a long time ago close, is that these studies, even though they excite people who like to write very big computer programs and run very big computer programs, they are useful if you can put them in relation to a very precise question, which is like a very precise drug, which you already know how it works on a very precise part of the brain, what kind of change that does. And of course, in a man, a person, is very difficult to say because you cannot make many many experiments on the poor fish of the lamprey. You could cut away all the muscles. That's called a preparation. So the fourth fish is just his brain and it's the spinal cord. And then you can measure all the signals coming out of the spinal cord. You can say, you do something and it starts to oscillate and make some changes to the motion. So this part of neural networks, which is, I would say, the biggest part of neural network in Sweden, I think it's the return in the investment in effort that you get in real improved understanding and use has not been that impressive. And the problem is more or less the same as in all of what used to be called, I think the term is already a bit not so fashionable, systems biology. You have big systems of equation, the action equation of something, and you have many, many parameters in these equations, and usually you many of those parameters you don't know. And at the end, it's difficult to establish what it means. Then, for the kinds of neural networks that we are talking about for learning machines, for machine learning, there have been many attempts to understand it from the viewpoint of statistical physics of disordered systems. There is a large part of the school that comes from Paris, with many people, the names which means a lot to me, maybe not to you, but anyway, who tried this. And I think they have, to this day, not really any success. They're not able to show any real interesting result on the systems that actually work. They always come back to much simpler systems which they can analyze. So I think somehow a new concept to understand these systems is what some new ideas, as radical as was Carnot in his day. That's the idea which I believe is true, and the hypothesis which I will put to you. We need something new to make some progress in the science of these systems.
Okay, thank you. Professor Gabriel.
Maybe you question some of the relatedness in the previous. In your opinion, what should replace the notions of heat and difference of temperatures in the new situation of the machine learning and artificial intelligence?
It's a very good question, and I don't know. If I do, I would work on it.
And the information.
Yeah.
Entropy is
Yeah.
joy.
Yes, maybe, but not clear that it had. You have often diffusion models, and there are models which somehow are built on. It's not clear that it's kind of the Shannon information that is the relevant. But what does it? I would say it's unclear. Yeah, but of course, so a picture in mind. Yeah.
Okay, thank you. There's a lot of questions.
Yeah, maybe.
Andreessen.
I will see it if, okay, say. Thank you very much for your very nice talk. I have a question about perspectives of thermodynamics that you mentioned. That's a lot of, do we need thermodynamics today? In quantum community, now people discussing such a topic as quantum thermodynamics. Yeah, are you familiar with this?
I work with it.
Okay, but what do you think about this topic, about perspectives of this situation? Could you describe it?
Yeah.
I will maybe explain, because some people think this is just a hype or something like this. So maybe not.
Yeah. Okay. There is the question is, let me rephrase the question. I think quantum thermodynamics actually started as a follow-up on stochastic thermodynamics. So the idea was, okay, now we know that if you have a classical system and a fusion system or a reaction system with discrete states, that you have these very nice equalities. There's its equality.
Yeah.
What happens if the system is quantum? That was the starting point. And the viewpoint on this one is that more or less it's true, but it's kind of trivial in those ones. But it has led to some interesting generalization in open quantum systems. So let's say in open quantum system, in the Lindblad perspective, what develops is the density matrix of the system. And if you want to consider quantum thermodynamics, in fact, it's not the state of the system which is your prime interest. Maybe you could reduce what you're interested in the load of the system, But actually what you're interested is in a functional of the evolution of the state, which is the exchange of heat between the system and the environment. And so you can theoretically, and you can verify things which you can also partially find in the lab, such that if you have a, let's say, qubit and it's connected to two quantum reservoirs with different properties, you can have at least a partial thermal diode. So the thermal conductivity is not the same in the both directions. Yeah, and that you can understand from the formulation, which is you can rewrite it in most cases as a kind of Lindau equation, but where the interpretation is a little bit different. And you can also do it in more general terms in terms of Feynman Bernoulli principles. I would be happy to discuss this second tomorrow. It's an interest of mine, but it's been dormant for a while. But yeah, but then there are some other theories which I know has been pushed by many people of, let's say, resource theory of, and then that part I'm not really familiar with, and I don't really have an opinion.
Well, that's what I mean, yeah.
I don't really have an opinion if it works, but it is a new direction in open quantum physics.
Okay, thank you very much.
Okay, thank you. Thank you. Out of our schedule, but it was really interesting. And I just want to ask if we need a long break or just a very short break. We change presentations and after that we will continue. So let's start for 10 minutes at 16:05. So please don't go far away. We will continue very soon.
Ні, це так. Ну там є. Можливо.
Can you imagine Mark and Sarah? Yes, now it's
I don't know. You can find that it's not. It's nervous. I'm nervous.
Yeah, no, it's that's really good. Yeah. Thank you, Professor. Very interesting.
Thank you for coming to the lecture.
Finally, is the very
You are now from the excited name of the ground state.
Boys here said they could change of.
No, what looks related point as well.
The point is,
Yeah, that's what. University as surprisingly wide range of but it's like it's separate. The literature studies of the science of not the law. So what can the relation is the one Yes. Even he is not advanced on this. He's trying to say, we will stop saying on this. This that is something that already is very time.
Let's start our small lecture. And for me, it's a big pleasure to introduce you Professor Carlo Bascigalupi from Scuola Internazionale Superiore di Studi Avanzati. Carlo is from the field of astrophysics and cosmology, and it's a big pleasure that Carlo is not the first time in Ukraine, and I'm sure that we will have a very exciting lecture about the challenges and opportunities in contemporary astrophysics and cosmology. So, Carlo, you have 1 hour at your disposal, but please keep some time for questions.
Okay.
Okay, listen.
Okay, I'm really honored and happy to be here with you and to be in contact with Eric, who just delivered a great conference, and with the colleagues of the Bokolibov Institute and the main astronomical observatory. As Sergio was summarizing, I've been here for this is my 5th time since the start of the war, and I bring you the message of organizations in Italy that are completely supportive of the effort of Ukraine, and I assure you that we are impressed by the level of organization, resilience, and determination in moving forward in the situation. And precisely because of this, I would like to take 1 minute to bring the message of Professor Roberto Iuppa, which is the coordinator of the National PhD in Space Science and Technology, that might be saying a few words in the beginning if I manage to get a connection. Let's see. Ecco, ok, grazie Roberto. Okay, so here's Professor Roberto Iuppa is coordinating the National PhD in Space Science and Technology, and we are coordinating with him and colleagues concerning this thesis, because in terms of exchanges and opportunities, we are happy to exchange, to be in relations between institutions and institutions, but we also like to engage international entities, and the National PhD in Space Science and Technology is a national entity in Italy, precisely dedicated to exchanges, to training of young researchers. So Roberto would like to say a few words in the beginning. Roberto, please, it's all yours.
Oh, hi. Well, I just see a lot of faces, so it's a pleasure to me. Actually, it's an honor to me to greet you on behalf of the National Program of PhD in Space Science and Technology. I know that I'm sorry, I'm voiceless, almost voiceless, but I know you are gonna hear Carlo talking about cosmology and the universe. So you're quite lucky, because Carlo is a wonderful speaker and pretty convincing scientist. So you're great time now. Let me stress how much we admire you, your strength and your commitment to do science and research, also in these challenging times. We are so pleased to see you attending this conference and this seminar, and pushing this collaboration. They really are eager to strengthen this collaboration, probably via projects that we can make together to increase the collaboration between Italy and Ukraine in these challenging times. So I'm talking about the national program of PhD. So thinking of joint initiatives like joint seminars, even for remote, if possible, exchange programs, probably also, in the next months or next weeks, and also some other scientific initiatives like applications to projects, other experiments, and then I would say initiatives in general that we could do really together. Well, this contact point, this Carlo, that again I thank for the opportunity now, and I think we have to exploit this occasion, because I think science is. I'm really convinced science is much stronger than any challenge we can face in difficult times. So thank you, and have a nice time with Carlo talking about cosmology. Thank you.
Thank you.
Thank you very much. Thank you, Roberto. Thank you, Roberto.
Okay, talk to you soon. Grazie Roberto.
Okay, bye-bye.
Okay, thank you. And now, restore the power, which is important. Okay, so we start our discussion. So I prepared a very informal discussion for you guys to survey the situation which we in astrophysics and cosmology. So many of these projects that I'm going to talk are shared with people in institutions in Ukraine, in Kiev in particular. No, we're trying to get together to get the coordination and the collaboration much stronger. No, we want, and I'm talking about these things. There is a little surprise in the end that I will show you. Okay, this is the the outline. So we are just highlighting the fact that cosmological probes are time machines because are probing the universe in different times. And then we just want to give you the idea of the roadmap in the sense of projects which are cosmology and astrophysics are now let's say engaging massive observations. We are in the middle of the observations of astrophysics and cosmological systems that will still started decades ago. It will probably last again for a few decades, and it's a great stimulus for theoretical physics, that is at the center of our attention. Okay, now and then something concerning the organization. What are the entities that may deal with this point? The international, how those organizations work, and then my angle is from my institute and from the National PhD in Space Science and Technology, and then we go to the conclusion to foresee the future. Okay, time machines in cosmology and astrophysics. The logos that you see around are the ones. The grants that we have, some are European, Italian institutions, European organizations, European grants. This belongs to this beautiful place and the institutes for which we are collaborating. We would like from these entities, okay, here to engage. We started already from CISA, and now with the National PhD in Space Science and Technology, we co-fund schools, etc. But we would like really to form more community with you guys because of the excellence which is here in these labs, okay, in the prestige. Okay, cosmology. Now, thanks to observations and some hypotheses, we have some idea of how cosmology proceeds nowadays. It is a time-oriented system. There is a past and the future, which in gravity is not exactly always like that, in which there is a very early universe, a very mysterious processes, and then basically after this moment in which everything was prepared in terms of inflationary expansion, then the rest is cooling. So that was very, very high temperature, and then expansion and cooling, in which you have first a dense plasma, then the radiation is free to move, then when the radiation becomes rarefied, gravity wins and forms stars and galaxies, and we have several snapshots of this thermal history. And so starting with and we have mysteries. We have mysteries. Mysteries are summarized in this, and they are disseminated into this timeline, basically. So one of the mysteries is the early universe. And this plot is similar to what Eric was showing earlier, but it is much more on the super simplistic version of what Eric was discussing. And as we were saying in the comment, the early universe is a picture in which this is a potential energy, and space has some transient energy that then goes down towards the minimum, then oscillates, and in the oscillation produces particles. Okay, so it's a super simplistic view, but it's so promising from the point of view of phenomenology that the cosmologists were happy. And they were making predictions out of this, and they are verifying this quickly. So as we were saying with Eric, it may be time in some short near future, together with the help of theoretical physics, to go back and re-examine the system, since it is so promising from the point of view of observations. First mystery. The second mystery is the other part of the name here, lambda called dark matter. The fact that the observations are helping us to identify the composition of particles and energy in cosmology, and it's coming out extremely funny. It is really funny. So only 5% of the entire energy business in cosmology today seems to be done by particles that we know, that we measure in laboratories, that we interact with. and so we measure in laboratories. The others are made by elusive, probably particles, which are heavy and create gravity, the rest of gravity in cosmology. They are about 7 times the known particles. That's a dark matter. They are heavy and moving slowly, so they are cold dark matter. Okay, and the rest of the system, which is about 68%, is in the form of even a more mysterious object, because in the recent billions of years, the universe seems to accelerate the expansion under the pressure of some unknown force, which is in the simplest verse the cosmological constant. Okay, so lots of discovery, no? All of these things here is lots of food for thought and for discovery. There is a huge potential concern. Okay, so that's the business. So it's the cosmology is disseminated by mysteries, despite of successes and progresses in observations, is disseminated by history. So we have the cosmological constant problem, what is the energy in the vacuum, which for quantum mechanics is generally different from zero. In cosmology, it cannot be different from zero, but it is tiny to make the universe accelerating, so it's a big mystery. So how, you see, if we believe in the early universe, in the inflationary business, so what is the physics, the mechanics of that, how the early energy which inflated the universe to these sides decayed into particles. We have no idea. Too much energies are too high. We are really model dependent there. It's difficult to investigate. We have a desert between those energies and the energies we can probe in laboratories. There's 1 TeV. These energies are 19 GeV. So it is a huge thing in which we don't know exactly what happens. And then how the baryons and antibaryons go to isometric, the leptons and antileptons go to asymmetric. And then what are the candidates, what are the okay, so disseminated. It's fantastic. This is presented as a success. It is a success. Okay, to be a few parameters to converge, but what those parameters describe, we don't know. They are certainly a representation of these mysteries. And these mysteries are the target, not the numbers, not the cosmological parameters. Okay, so no, and this is room for discovery. You know, the analogies with the atomic pile by Enrico Fermi in the basement of Chicago. No, and no, that's the arena of discovery. Whenever you have those mysteries which are popping up in terms of parameters that you are fitting, etc., and you have no idea of the physical properties of those entities, then you may expect big discoveries. No, especially if you are not touching things, very sensitive things like how the vacuum get together with energy. What is the energy density in the vacuum? It's a complete history. So there is a potential for discovering in these things. Okay. Okay, now see, okay, super simplified ChatGPT plot over here, no? So
The very simple earlier once again. So this is statistics.
It's me.
okay, we continue.
So
Yeah, absolutely. Yeah, absolutely. Okay.
If something happens, we will see.
Yes, in the 90s, when I was finishing my studies and starting the PhD, etc. No, cosmology was dominated by theory and models. No, and so we were playing with the potential energies of the inflationary fields. You know, doing models of the. Nowadays, the situation is the opposite. No, as a young researcher, I see many young researchers here. What happens is that a physicist is not an isolated mind, and no, the way you have to also to adapt a little bit the era that you are facing. No, if you are studying like this, you have less resources and more models, etc., etc. Today, no, physics in cosmology and astrophysics, ask young minds to engage into problems of statistics, to understand the systematics of instrumentation, how to disentangle different emissions in the sky, okay? And so, the stimulus is not just, the stimulus of being a physicist is in us, okay? But then it has to also to face, to be interfaced with the problems, modern problems which are there. And now, it is the era of data in cosmology and astrophysics, and it will last for a few decades in the future. Talking about data, this was mentioned already. How not to mention this aspect? We have to mention these aspects. These things are entering in our life. As the Bogolyubov Institute director was stressing this morning, and we are talking, the director in the ITNU in Tokyo was also stressing, these systems are getting to a complexity, and Eric was mentioning these things in his beautiful talk. And the mystery of complexity, deep learning, the world consciousness was also mentioned in this part. We have no idea, exactly. We know these things. We have to talk about these things, and academies are places in which it is beautiful to talk about these things, because we have the intellect, we study all the subjects, we have to interrogate ourselves on how to engage the new situations. Academies are a beautiful location where to discuss about these things. Here in this talk, we can just say that to answer these questions that you can compare. These are the answers that were given by the entity. Just 1 year ago, I think. So I should update those. But the entity responded, making a comparison between the system. And so here, we cannot get into any detail, but we can say just the numbers. We see that numbers of neurons and synapses are starting to be comparable with numbers in the system. So since we know that complex mechanisms are emerging from this in this system, we have to be prepared that maybe different but equally complex mechanisms may be emerging from these entities. Okay, so we have to be open-minded and check and be aligned with the development of these things. Aligned. The word and other dimensions is alignment. Okay, but open-minded. So numbers are getting interestingly comparable, and so it is good to keep an eye on these things while we exploit this huge power that is at our disposal nowadays. It is, of course, also in astrophysics and cosmology, spreading like okay. Okay, fine. Back to our business, cosmology, the Big Bang, and then different epochs, etc., and then the present, in which the inflation, and then particles form, and then atoms, and then cooling, and then galaxies and planets, and eventually life. So this plot, which is cumbersome, and so you have so we basically describe the system with numbers, and we try to isolate the part in which are mysterious, the early universe, and when the universe was 10 to the 28 at least times smaller than it was today. Distances were 10 to the 28 that it was today. And also we have some processes which happened, the equivalence, the formation of the relic radiation and others, and then structure formation, in which the dark components are playing a major role, matter and energy. So nowadays, what is happening for cosmology and astrophysics, it is not anymore the analysis of the system as a whole. No, they do. You can talk to cosmology. They pronounce the word tomography many times. Tomography, because observations are so powerful that now we can study the universe independently into shells. Okay, of course, not taking into account the correlation between shell and shell, okay, but the statistics is such that we can do cosmology here, cosmology here, cosmology here, cosmology here, cosmology here, and eventually also cross-correlating with other fields, cosmology. Okay, because no, and so in this manner we can, for example, in this graph here, reconstruct, measure the dark energy abundance, not as a single measurement from the entire universe, but in different bins in redshift. So addressing what cosmological constants. The Euclid satellite that later we preview is doing precisely this aspect. So the observations are powerful, very good. We don't do any more cosmology in a single system, but we do tomographic cosmology. Okay, it's a system forming the structures. We basically go and scan it like a radiography, the tissues.
Like X-rays.
Exactly. So that we do, that's a modernity of the approach to observation. We are tomographic at this moment. Okay, so we place time machines, and the first time machine for observing, doing this tomography is here, 100 seconds. Okay, and here, proud of quoting this aspect. This boy, this nice curious boy that we will have to protect the kids from deviancy in these years, is George Gamow, Ukrainian scientist, 3 years old in Odessa. Okay, that person was later, a few years later, was a physicist, which was in the 48. No, they were atomic physics. They were studying, of course, nuclear reactions, because there was a nuclear atomic energy from the International Energy Atomic Associations also. No, and at the time, this expanding universe was pretty much competing with the idea of the steady state universe. And so he was curious and reading those papers of those funny guys with the expanding universe, but which by joke were called the Big Bang. The Big Bang was a joke. They were calling a primeval fireball, but the Big Bang was a joke by the steady state physicists which were kidding with those guys of the expanding universe. And he was saying, okay, if the intuition was if the universe is expanding, then we reverse the time. There was a moment in which everything was very much high density and compact, temperature are going up, and so the universe was in permanent thermonuclear reaction. And where is the gamma radiation? Disappeared. So they calculated, and more or less with the time of recession of galaxies and the amount of time they could measure, and they predicted that thermal radiation from the early universe or the Big Bang should be still present, in the form of very rarefied, very diluted, but still present, and in the microwave, so very low energy because of these guys are Penzias Wilson, Nobel Prize for Physics, and they were testing an antenna for communications of satellites with satellites in the 60s, and to make the story short, they found an excess of power independent from the directions. They tried to clean the antenna in any manner. They were curious. They started to write a paper of the possible extragalactic origin of this excess. Okay, and this thing came to the attention of nearby physicists in Princeton, and they were identifying this as one of the major discoveries in physics, in science of all times, basically. The discovery of the relic cosmic microwave background, the thermal radiation, which is proof that the universe was in a very high density, high temperature state in the early times. So the appetito viene mangiando, we say in Italy, which is the appetite comes when you are eating, basically. So cosmologists immediately started to study. They said, that radiation is very ancient.
coming from the cooling of the system and then being free to travel to us. Okay, excellent. But then we should be able to spot structures. No, in this radiation. It should be like a snapshot of radiation coming from the early universe, bringing us the details of the structures in the early universe. Like when we saw a cloud, we see a cloud, we don't see the interior of a cloud, no, because the opacity is such that you cannot get light, the image of the interior of the cloud, but we see the surface of the cloud, which is structured, no, same here, but this is the universe. And so, no, from that point, they built tens of telescopes and 3 satellites, and we are working on a fourth one that we will be mentioning. We have the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probes. It was in the 90s, in the early 2000s, and the monster of the European Space Agency, Planck, which ended the operations in 2014. And these are various pictures of these things, and the beautiful progress of technology in the capability of these satellites to isolate, to improve instrumentation. That's a beautiful process, no? Progress, no? That's a beautiful progress with instrumentation, with very good motivation, no? Other motivation for aggression or violence are not the only motivations to progress in instrumentation. So in instrumentation, we can progress even with pure science, and you see those things. And so I skip the history of, I just want to focus you because I need to tell you something later about the European Space Agency engaging in these historical meetings for building this monster here, which ended the observations in 2014 after the other 2. And these objects, these are observing from a location which is beyond the moon, and there is history concerning this part. And to give you a preview on the organization of these systems, you can imagine what it is to build a spacecraft. And then it takes more than a decade from the initial idea. Then you have to convince everybody, then you go to the agency, you start the construction, and then between 10 years and 20 years since the original idea, you launch the machine. Okay. And it is a complicated objects with many entities, many space agencies, different instruments, and the scientific targets that we have. When the satellite operates, there is a complex, what we call the science ground segment. So the satellite is just a probe deep into space, collecting data, and then on Earth, a segment of that object on Earth is dedicated to the data analysis. For Planck, it was 2 data centers, the low frequency instrument and high frequency instrument, and which were coordinated by Planck Science Office, which were in contact with the mission operations. I'll tell you later what are these pictures. Okay, the various levels. Okay, and this is the kind of progress that is amazing. That's a masterpiece of science. Okay, and so in the 90s, the Cosmic Background Explorer was able to isolate the first measurement of detail in the relic radiation. So the relic radiation coming from the Big Bang was not uniform. It was remarkably uniform, okay, but they managed to be so precise to reach 1 part over 100,000 precision in order to spot these vague differences in which the green part are the ones in which the temperature is about, the intensity is about a little bit higher, the blue part is, the intensity is a little bit. And are we happy with that? No, human beings are not happy with that. The vague detail is because the instrument was limited. Then you build better instrument. No, you do a lot of research on instrumentation, etc., and you get a little bit more focused. No, actually, not much more focused. No. And then 2003, and then what you do is you do even more radical situation. And this picture is from Le Figaro. Okay, it's a beautiful picture. You go with Planck, which is at the limit of the angular resolution which is possible to get. And you see this image of the early universe, in which the little spots are the ones which in which the temperature is a little bit higher than the background, and the blue spots are the ones in the change. So variations here are exaggerated. Variations of the intensity of the temperature are at the level of 1 part over 100,000. And this is the early universe, the baby universe that was let's say, releasing the radiation when the temperature dropped to 3,000 Kelvin, more or less. Okay, that was the moment in which radiation was free to move, started to travel, and we received it with this global distribution of the intensity. Okay, not only that, nowadays the frontier is not the intensity, but the light has linear polarization, because it is the Thomson scattering making scattering the electrons to us. And so there are differences in the polarization, which is revealing of yet new processes that we can study. So the information is not only a number, so the intensity in each direction, but also an angle and the intensity of the polarized radiation. And so that is under scrutiny right now, because of the reason that we are saying. Now, coming back to data, this is a fantastic challenge for data, for physicists, statistics, data analysis, complexity, because you start for CMB measurements, you have on board thousands, tens of thousands, 100,000 detectors, which measure the sky radiation many times per seconds for years. Okay, and then you put those numbers on an enormous line, and then you use algorithms to bring those numbers to sky maps. So you do the first compression, and then you take those maps to feed, and you feed for the statistics that you can extract from those maps, and you feed for cosmological parameters that in the end they become numbers, the famous cosmological parameters and measurements that you find. But it's a history of a huge compression of information. Okay, of course we have to, when we increase our grip on data, more extended data sets, we have to check to address statistics. Now, the Moore law here in the representation of the intensity of various experiments, accuracy, sensitivity going better and better and better and better. With the ear, we have to pay attention to this, to the slope of these curves, because those are measuring the time in which we, as a species, we are getting ready for analyzing bigger and bigger data sets with better and better accuracy, and also they relate in the third axis here. There are computational facilities as well. So those things are impacting several areas, which are theoretical, technological, analysis, and many others. Okay, now we explored this part. We go more recently. We place a time machine over there. And this time machine is the Euclid satellite. The Euclid satellite is represented by the Euclid Consortium, okay, this huge community here, which wants to analyze the data of this object. And this, some of you have already seen, these are the measurements that have been just taken a few months ago. The satellite was launched in 1st of July of 2023, no, and commissioning, travels, etc., and then starts to analyze. And of course, instead of looking at the early universe, now in those more recent epoch, the satellite looks at formed objects, so galaxies, and these are one. This is one of the image that you see, and for just first images. Okay, that's it is a few data in magnitude. In dimensions, these machines are basically tall as this room here. Okay, with the size, a diameter which is 3/4 of the height of the roof. That is the dimensions of these things. And even for this, there is a huge organization. The consortium is made by 1,000 scientists with many working groups, more instrumentation, more theoretical. And this is the schedule. So for why we want to collaborate with the global community, and in particular with Ukrainian scientists, because the information here is huge, and the time scale is huge. It extends much more in the future, pretty much in the future with respect to the madness which is ongoing. So it is very difficult, but we want to have the vision beyond this madness, and to we are convinced that the madness will go away. Okay, and what makes sense remains, and we want it is a difficult task. So we need help. We need collaboration, good collaboration for these things. Okay, 8 years, but it will be probably since the launch. That brings us to 2031, but I think it will be probably extended for another 3 data releases. So you can, there's only for this satellite. Okay, there are papers and results. You can find on the web the data release 1 area in which you see this region of the globe is being surveyed with amazing resolution. So the status is such that the machine is working extremely well, and it is making several snapshots of the universe, the late universe, in different tomographic slices for measuring how the dark matter and dark energy behave. This is a plot for the various coverage of the sky in the various years. Okay, organization of the ground segment. As for the other satellites, these things have ground segments. And the organization of the European Union for making all the various organizations and the various countries in terms of contribution, the distribution of help that we can get. Now, it is a big effort to design, prepare, construct, launch, analyze, interpret, and this is just one of the efforts which is ongoing. So that later we see the roadmap, and we see there are many. That's why we want to collaborate. We want to become more integrated. So also for this situation, the story is a huge compression. In this case, the satellite looks at galaxies. The galaxies are pixelized. And then science is done by analyzing all the signal in these pixels, so reconstructing the shape of galaxies, counting them in different slices in the universe, observing their deformation because of the effects like gravitational lensing, and infer cosmological consequences. So here, compression again, and also they go into continental archives, because in the end, that's public knowledge. In the end, everything which is discovered, even the tools, the algorithms, the codes to analyze the data, go into public archive. okay, which are handled by the European Space Agency, okay, and now become objects to everybody. So it is a very challenging, no, and also sometimes inefficient but beautiful cycle, no, in which there is the idea. You get resources, you get support from agency, you go to observations, you do amazing construction of the machine, then you launch it, you analyze for years and years, and in the end, the information goes to everybody. Okay, it's a huge work. And there are many of these projects that we see in a moment. So that's why we want to collaborate. And from the parameters, you can also have, of course, discoveries and ideas and then discoveries. Okay, we go back. Okay, we are now starting to look at the future now. Okay, we go back to the early universe. No, is the work with the relic radiation of the Big Bang over? Well, no. So next, I'm proudly here now. Next, so I'm going to Warsaw in Saturday, taking a flight to go to Tokyo, where the Japanese Space Agency takes the lead in the 4th CMB satellite, which is dedicated to polarization and wants to measure the polarization of the cosmic microwave background with extreme accuracy. And the reason is that without going into the details of this plot, the polarization of the radiation coming from the early universe is the polarization. So it is what we say a tensor. It is a rank 2 tensor, we say. Okay, so it is composed by a field which is derived by the gradient field and the curl component. The curl component may be excited by cosmological gravitational waves. So if the early universe, the Big Bang, the inflation, the mysterious process that we were highlighting, not only produce oscillations in the density, but also stretches space-time, as we hope, it should leave a unique imprint into the cosmic microwave background polarization. Very small, but detectable. And so that's why they are building a 4th CMB satellite, to catch space-time distortions in the early universe. Okay, so that's matter of when, not now. That's the next decade. So probably the second half of the 30s. So this is for a young physicist which is approaching this system. No, that's a timeline which is perfect, guys. Okay, and not only satellite, but also telescopes are already on the ground to do the same job from the ground. Okay, so this signal is being pursued from the ground on top of mountains in the Atacama Desert and from space, Science Observatory and Albert. These things are, of course, making agreement to each other because they are making the same, looking at the same. Okay, I can even show you preliminary. The satellite is for the next decades. This observatory started the observations, and I can even these are examples of preliminary data from the previous Planck satellite and the new measurements, which are clearly highlighting the same structures. And this is all public, but even I invite you to go into here and see the progresses as they are happening. And those machines are working again. Huge instrumental progress. Okay, now we are going to the last third of our discussion, and now what is happening from now? What is happening now, and not what is happening in the next decades? Okay, that's very incomplete also. Okay, the disclaimer is that this is only from the projects that I know. I don't know about the intensity mapping in the radio surveys. I don't know about So I know, but I'm not an expert of surveys for projects for surveying, investigating active galactic nuclei, exoplanets, astrochemistry and astrobiology, solar system exploration. So each of these area is comparable with what has roadmap, which is comparable with what we are about to see. Okay, that gives you an idea of how big is the information, how coordination and global collaboration is needed. Okay, so in cosmology, in the projects that I know, this is the situation. So we are here with Euclid and the Rubin Observatory. We have surveys operating in the radio band. We have the Simons Observatory operating. We have other probes, the Atacama Cosmology Telescope, Southwell Telescope, the Simons Array, the Keck Array, and Simons Observatory operating from the ground. In space, we have Roman satellite, which is about to fly, JWST, Euclid, which is observing, and then we move forward. Now, in 10 years from now, we'll be having Roman observing, Lightbird, and the Advanced Simons Observatory and the Southwell Observatory. Now, each of these objects has a complexity of one that I showed, Euclid or Planck. Okay, so it's a huge complexity. It's huge opportunity for communication, progress, science, intellect, freedom, no, and beautiful motivations. Okay, not nightmares, beautiful motivations, not deviancy. Okay, we have enough problems to solve to engage the systems, no, and so we have to clearly. So the systems which are deviating from what makes sense, which is knowledge for everybody, are deviant. We have to marginalize them and eventually dismantle. Okay, this is not all, because now there was the discovery of gravitational waves. So we have Virgo is operating, then the Einstein telescope and LISA satellite, the system of 3 satellites, is being prepared for the next decade. No? Okay, so and it is only for the project from my angle. Okay, all the other areas have similar roadmaps. Okay, in terms of number of probes. Okay, what about the international organization? How that works? Well, this is your business of the universe. Then you look at the universe, you have some idea. Okay, and you are here. You are in the same community, and you look at this system, and you're thinking, how can I observe maybe this probe will observe, and you are. Okay. While the ministry and the funding agencies are, the government and funding are discussing, and they interact, they exchange resources. Now they do their own business, they administrate other area of system. Okay. Okay, to show about how, okay, this plot here is an estimate of the budget for cosmological observations with respect to the entire MFF of the European Union. Okay, so for cosmology and astrophysics, let's say. Okay, and you see, this is Europe. Okay, and so it is small. It is 8% in terms of money, but it is not entirely negligible. So it's good. It's not could be larger, but we understand that there is more spending to do in many other areas. Okay, but this is a non-negligible fraction which goes into these beautiful projects. No? So you have the idea, no? And when you have the idea, you go to this system and you start, say, telling them that you have this beautiful idea, that you have this mystery to be investigated, no? And usually they ignore you for a while until you insist. No, if you are motivated enough, you insist and insist and insist. No, because in the end they want to be convinced. They want to be convinced. No, and especially they ask, what is the mystery you're investigating? This is very fascinating. But they start to ask you, how much does it cost? And more or less, you know, and then they say, which kind of instrument in industry are you thinking to involve? Because knowledge is beautiful, science is beautiful, but they also want to invest the money into research for new technologies, new instrumentation. They want to give money to companies constructing various pieces of those probes, and then become objects that we use every day. The CCD, which is the cameras which are in the phones, where their creation, the CCD, were stimulated by astrophysical observations. No, nowadays it's with us, no, and we enjoy those things. Okay, so now there is this debate, no, and then eventually, no, when they are almost convinced, they give you the green light. They start to support your project, no, and it's a back and forth of the money, and then they also review you. No, there is a part of the funding agency which is dedicated to your to review if you are working or not working, progressing or not progressing. No? And in the end, what is this situation, this system made by agencies, the government, and the science community makes this present, which goes to everyone. Okay, and this is an extreme synthesis, oversimplified, but it is the virtue of this mechanism, which is good motivation to do instrumentation, to struggle, to be together, to see coordination. That's a beautiful part that we all need to. Now, is this realistic? Well, no, that's debatable. No, how this super simplified process is projected into our system. No, this is just a representation of space agencies in the world, no, and there are no significant fraction of the planet which doesn't have any space agency, no, and some others have advanced space agencies, and some others have preliminary space agencies. But what you see in this figure is the level of fragmentation, especially in Europe. So many fragmented systems. So now you can imagine what is the challenge in making everybody to communicate in a big project. We'll come back to this image later. Okay, and accidents happen along the way. No, I have a few of those accidents. The Planck crisis, one. Planck satellite. This is so the Italians, messed up completely the budget, and so they were short of I think 50 millions with one instrument on board of the line. So we were desperate now. So we went to the ministry and said, please, can you pay? We messed up, but next time we'll be so good. And the minister said, no, you guys messed up, no extra money. And so we almost risked to cancel the mission. Okay, and there were Nobel Prizes, George Smoot writing to the president of the United Space Agency, begging him to increase the budget because otherwise it's dangerous for the mission, etc., etc. No? And the guy was saying, no. Okay, and so in the end we canceled one frequency channel in Planck, but Planck flew anyway, and it was working fine. So very tough decisions for principal investigators, no? Deciding to be picky and say, oh, we cancel the mission, or to say we go on with a diminished mission. That was tough times, which I remember. The Planck crisis too. This is fun, no? Planck, was supposed. This is a ground almost fatal. No, this is in flight. So as you know, the active cooling, the satellite has to cool down, and then soon after launch, the cryogenic chain was activated. So the satellite started to cool because it has to be extremely cold to measure correctly. No, and then so there was the moon. Okay, the satellite was passing beyond the moon, and it was cooling before entering the shadow of the moon. Then we lost contact because it was on the other side of the moon. And then when it went back into contact, it was heating up again. So what do we do? So the cooling chain was interrupted. So no, if that doesn't work, no, the mission is over. No, there is no way to recover. So I discovered this when it was already done. Okay? But there were a few polls, no, and there was a disaster, no, so they don't understand what's happening, no. So in the end, the ultimate decision, shut down and restart. Like we do with phones. Okay, and so with the principal investigator crying, so please, sir, my satellite. Okay, so it's 20 years of my life. Okay, and so they shut down and restart, and the satellite started to went up again and restarted the cooling. Correct. Okay, and it never happened. Okay, so the satellite went to temperature and stayed. Okay, that was a crisis. Okay, and that is what may happen. Some historical remarks of what can happen in this very complex system. The cryo crisis of life. The Ukraine crisis. Russia invades Ukraine. Okay, this is particularly so.
Carlo, you don't need to sacrifice yourself. We appreciate your innocence. Please put on the coat.
And the coat here. No. I'm fine because I'm moving. Okay. Okay. So and this is a markedly bad event for specificities. No? So when this situation happened, a clear sign of the failure of the Russian organization, okay, deviancy of is that suddenly all the various bodies of the system immediately become hostile. Okay, so the government does a crazy thing, and also the other bodies like the Roscosmos becomes hostile instantaneously. So Ukraine was supposed to fly on the Russian launcher, and the Russian space agency disappeared completely, started to be very hostile. No way to talk to them on any manner. Very hostile. So we said, what do we do? What do we do now? We are doing this. The satellite was ready. That was 2022. Satellite ready in a garage. And now it is, you can imagine how much it is expensive to keep a satellite ready in a garage in terms of warranty, maintenance, etc. So the principal investigator was really desperate and say, what do we do now? We are launching. So and I remember already that in the consortium meeting in April 2022 in Oslo, they were saying, we don't launch and we need to say, and we go to Ariane, but the Ariane is the European launcher, which is not even ready now. Okay, but there is a line of silence. So what do we do? And so we'll see. We have to make a tiger team to investigate this issue. And already in the audience, I remember that nobody was raising the hand of and proposing, but there were people saying, ask SpaceX. Did they ask the SpaceX? Just mention, whispering in the Then later on, the PI, the principal investigator, announced a global survey of launchers. Okay, we are going to inspect all of the launchers in the world to launch Euclid as soon as possible. No, we will conduct a study that will be concluded within 2022. No? In December 2022, we'll get the announcement. So already in the summer, we got in a management call, and the principal investigator, which is Yannick Méliès, which passed away just a few weeks ago, unfortunately, he was saying, we are going to launch with Falcon 9, SpaceX. Okay, and we contacted them, they are happy, they made vibration studies, and they asked us to change the attachment of the satellite to the launcher, and that's it. So we're going to launch. So please no, this is secret. Don't tell anybody. No, no, no. Okay, and said, sure, not saying anybody, not telling anybody, just happy, etc., etc. Then I hung up. I went out of the corridor, and my postdoc came to me and said, "Is it true that we launch with SpaceX?" So you see, okay, so we launched on time on July 2023, and since then the things together with crisis, there are also beautiful organizations, the Italian Space Agency getting together for supporting the LIPER satellite under the president of Pakistan, which was the former coordinator of the national PhD in space science and technology. Okay, now we go back to this part. We are going to the conclusion. Yeah, we are concluding, and so given this situation, what you can expect is that the future of cosmology is tomographic and probe combination. So everybody is connecting with everybody here, because in many science respects, they need the data of the other guy to do good science. So there are increasingly memorandum of understandings being subscribed by those various communities. Okay, my angle, okay, on this system for young researchers and physicists. Okay, my angle is in the International School for Advanced Studies, which want to, it's here. It's very close. And we want to promote internationality because we need help with those projects, because either we get in a global good community, now which orient resources toward beautiful, meaningful targets, or no, we risk not to optimize all the information that we are accessing to observations for theoretical physics, for statistics, for algorithms, for data science, etc. So the school is 50 years old, and it has it is but international, and so we have yearly PhD courses. As a PhD entrance, so only the astrophysics and cosmology, 5 PhD positions per year, together with the astroparticle makes 10. Okay, in this situation, as we were speaking with the director this morning, the challenge is, so we are very happy to share resources. The challenge is to keep good, strong community of scientists at all levels in Ukraine. So no matter from where we get the support, we need to keep institutions in Ukraine very well active and supported. Why? Because it is just because we are good guys? No, because it is needed, because we need more centers for all these observations. No, and we need those. So we need to make these things robust. Okay, and I wanted to go to this. My second angle is the National PhD in Space Science and Technology. This is a national entity that Roberto Yupo was presenting earlier, which have 7 curricula. You see solar system, observations of the universe, which is mine, planetary science, astrobiology, space-based, satellite, space economy, and diplomacy. This is also a number like 30 PhD positions per year. Same story. We are happy to engage into PhD projects, but we want co-supervision and massive stay of students and us visiting Ukraine for extended periods. No, because it is our own interest, not just because it is the right thing to do. All right, we conclude. The decades in the near future. If you read the European Space Agency Voyage 2050, it is full of marvelous ideas and projects and things. So the era of observations in this business of space technology will continue for several decades, from now to several decades. Okay, and this is the final remarks that we already stressed. We want to come back with this business and think. So those projects are beautiful, and each of them is bringing theoretical investigation, organizations, coordination, fundraising, resources, constructions, companies, launches, space travels, analysis, interpretation, and back to theory. Okay, the question is, are we ready to engage such a, to which level are we ready, or such a pressure from science? Is it beneficial for this fragmentation? Well, we know there are accidents, no? There are accidents. No, one thing has basically committed suicide. Okay, so they disappear. I can tell because I know we not only you guys, but also in Italy we had collaborations. No, it's completely destroyed, completely gone. No, they will face some judgment which is not in our hands to handle. Okay, for what is happening. Just from the perspective of space science, they're dead. Okay, and something else is happening. And this is the surprise that I wanted to give you. So it is a recent news that the Ukrainian Space Agency has joined the European Space Agency. This is a huge fact. It's part of the cooperation that we want to implement. Okay, and it is important because the European Space Agency is very inefficient, very slow, very you need it moving slowly. But when it does projects, they are milestone like Planck, Euclid, and in LISA in many respects. And so this cooperation is probably extremely valuable for this situation. It's a new fact that we really welcome at this meeting. Okay, so this is my last slide. So are we ready for engaging this huge amount of observation, of information? Science-wise, yes. Curiosity, we are curious, yes. No, we are ready for surprises, yes, we're ready for surprises. What about the organization? Funding agencies are there, but they are very much fragmented. No? And more technology for these things and less for wars would be much better. Would be much better, together with avoid abomination. Okay, so coordination is challenging. It is happening, coordination in countries which are non-invaded, and also countries which are invaded by deviances. Human resources. Yeah, we have some good support for human resources. We have also to take into account that we are not compensating all this information with artificial, with digital entities. We need human nodes with human brains, to tackle this system in order to get out of. So together with investments in technology, investments in projects, we also need the proper way of keeping people and nodes and universities and kind very well alive and supported by resources. And with this, I thank you.
Well, thank you very much. So, dear colleagues, now time for questions. We had was an very interesting lecture and a lot of good information. So please,
Eric,
please.
Thank you for a very rich and a lot of stuff. So not easy to follow everything. Can I kind of continue on something we said during the meeting with the coffee?
Yes, we can.
Yeah. So, what's your view on this current, very recent controversies? So, is there dark energy or not, or what is dark matter? I mean, what's the state of the art now, really?
It's
the state of the frontier of the science.
Yeah, it is a very good
accelerating or not?
Now, it is that's a very good question, and if the subject we are addressing were ordinary, I would say certainly yes to your question. The universe is accelerating the expansion. We have several independent evidences for that, and we are pretty much confident, and we'll see what it is, etc., etc. Now, the caution is the fact that according to the two visions of physics, the vision of physics that we have on what concerns space-time and gravity, and what concerns quantum mechanics, these things about the universe, the accelerated expansion of the universe is driven by energy in the empty space, in the vacuum. And that is one of the greatest mystery of physics since the start. So we don't know exactly how to treat that entity. We have no idea what it is exactly. So the story of the cosmological constant, the vacuum energy, starts with Einstein, okay, trying to put some energy in the vacuum in order to keep the universe static, and making the biggest blunder, as we know, and trying to say, no, that's a mistake, let's take it out. And then quantum mechanics predicting generically non-zero energy density in the vacuum. By how much? By any reasonable number, any reasonable density would make the universe to go in inflationary expansion in less than a second. So no, you don't want to. So we say, theoretical physics said, even they invented supersymmetry to say, no, the universe has zero vacuum energy. Okay, now it seems to be very small, but non-zero. And so it is an embarrassment, beautiful, a very healthy embarrassment for physics. So we don't know exactly what it is. I would, I think we should expect a major change in the understanding of this, of what is vacuum energy in general, and its manifestation in cosmology in the long term. How long? I don't know. What they are trying to do, and that comes to your comment, is that the latest measurements from pre-Euclid telescopes are reporting an indication for a known constancy of the dark energy. Okay, the DAISY data release 2. Exactly. Which would be suggesting as it is that the dark energy has some dynamics, which means it's not a cosmological constant, something else. It's a fifth of force, quintessence, etc., etc. Now, do we buy those indications immediately? Well, with some caution, because of several reasons. Because the evidence is not super dramatic, first, and second, because if the dark energy possesses a dynamics, then we cannot model it without taking into account spatial structures in the dark energy. Now, in general, it is prohibited to have something which is non-homogeneous in one coordinate and not in the others. And that is where we are starting to be model dependent. It's very difficult. But if what we can say is that if that evidence persists, then we have to go to theory. We get ci rimbocchiamo le maniche, and we get back to theoretical work to come out with models of dark energy which are coherent, including spatial dynamical, but including spatial perturbations, to be compared with observations. Okay, and that is probably something that it good activity for the next couple of years.
Thank you very much. Other questions?
Are the theories that consider dark matter and dark energy jointly
Mhm.
preferable
Mhm.
or not?
We don't know. There are models that it is tempting to relate the two, into even imagining a coupling concerning the two. Preferable or not, I don't know. I know that there are modified gravity parameterizations which are trying to relate the two, introducing an explicit coupling. An explicit coupling comes with extra parameterization, which has to be inserted into the equations for cosmological evolution and compared with observations. So even that one, especially if the evidence from DESI data release 2 persists, will be addressed for sure.
Any other questions? May I ask, okay, please.
Thank you, Patrick, for your lecture. Thank you for coming here. I have a question. What can you tell about the experiments to search for neutrino mass? Since we know the oscillations of neutrino from Gamma Libra experiment, I'm not wrong. And what about other experiments, maybe non-direct searches for rare processes that can say something about the neutrino mass?
See, that I didn't mention that, but this is one of the major joint goals of particle physical experiments and cosmology. Neutrinos, the mass of neutrinos, total cosmology is only sensitive to the sum neutrino masses, not of the hierarchy. And the sum of neutrino masses contributes to the statistics of cosmological perturbations in the structure formation regime, so from tens to hundreds of megaparsecs. Okay, and no, it is cosmology is constraining the lower limit from particle physics for particle super Kamiokande, for example, and the cosmology are getting very, very close. So the hierarchy must be living in a small interval now. Even for that, independently of what I just mentioned, there is hyper Kamiokande under construction, and they will be trying to solve for this, to find the balance between the two observations and also to identify the hierarchy, if it is straight or inverted. So it's a super major target, neutrino structure layer.
I just want to ask, I know that there are a lot of discussions about candidates for the dark matter, and one of them is stereo neutrinos. Yes, and I noticed that one paper published recently where it is stated that this candidate is not anymore the candidate. So can you comment something about this? This is
sterile neutrinos. Sterile neutrinos. What to be honest, I would wait until saying that these things are disfavored by observations. No, because for instance, the DESI measurements for the dark energy dynamics are correlated with different other experiments. Now, in the probe combination, they never report a cosmological constraint with one measurement only. They combine the other data sets, and all the other data sets are assuming the neutrino three families with no sterile. So it will be very interesting to investigate how those tensions in the data sets react to the presence of a population of sterile neutrinos. No, because anomalies in the data sets, like possible evidence for dynamical dark energy, motivates the reinspection, not only dark energy modeling, but also other things which may influence the data set in other manner. Okay, so I would really keep keep attention open also for
Thank you very much. Yes, please.
One more question. What's your opinion? Can string theory help in finding the real candidate in dark matter particles?
Well, that's a very interesting question, and it is at the core of something which is very difficult to do, and which goes into one of the first things that you mentioned. So we have basically a kinematic description of the early universe only. So transient vacuum energy that has to decrease in time, and then when it reaches the minimum and oscillates in the minimum, then the universe slows down, and eventually the decay rates of this inflationary energy, which might be related to strings or pre-Big Bang phases, or how to convert. So we have totally no idea of the couplings of this early universe energy into the other particles. We don't know mechanisms. We don't know even the products of this decay. And because we have at least 17 orders of magnitude gap of those energies at which those things happen, and 1 tera electron, which is the electron with symmetry. So we don't know. I don't know how to investigate this thing. I don't really know, because those energies, apart from the phenomenological description that we have from moment, are very much difficult to access directly. In principle, when inflation ends, when the vacuum energy is vibrating around the minimum and start to decay, then there you might see signature of the coupling of this vacuum energy with the products. And but that is very difficult, because those are the final stages of inflation, and the scales at which things are produced are very small. And on very small scales now, today in the universe, we have black holes, planets, stars, galaxies. It is very difficult to read initial conditions in these systems which have been reprocessed. So it's very difficult, very difficult. Very difficult.
Yes, thank you. Other questions? No questions, so let's thank so beautiful lectures today.
Thank you.
Thank you very much, and we enjoyed a lot of your lectures. Thank you.
Thank you.
Yeah, so we close our seminar. Thank you for each participating.
Thank you very much. My hope is that